Hello, this is lecture 8. In the previous few lectures, we had derived the conservation of mass and conservation of momentum, and we have also seen how the rotating frame of reference and non-inertial frame of reference brings about a change in the momentum equation. Now, from this lecture onwards, we will discuss the equation of state. Okay, so this equation, will see the necessity of this equation of state. So this is the equation of state that we'll discuss today. We'll start discussing with this. So this is necessary because we need to provide a relationship between density and pressure. Need a relationship between density and pressure. And this is required to fully describe the fluid system. And this is the equation of state, and this is called the equation of state. Okay, so this is the relationship between density and pressure, is called the equation of state. So in an incompressible fluid, this is a simple relationship. By definition, incompressible fluids do not change their density with pressure. So for incompressible fluids, rho equal to constant. Okay, it's a simple statement. Okay, in a single component system. In ocean, however, the density is a function of temperature and salinity. In oceans, density, now it's a multi-component system. Density is a function of temperature and salinity. Okay, so we need some functional form between temperature, salinity, and its contribution to density. In most cases, for most cases, density can be assumed to be linearly dependent on temperature and salinity, and this is probably most of us have done it in our higher classes. So we can write the form of the density as a function of temperature or salinity, something like this: rho equal to rho naught 1 minus alpha T minus T naught plus beta S minus S naught, where rho naught is a reference density, T naught is a reference temperature, S naught is reference salinity. So this, as you can see, this is a linear relationship between all the three quantities. So T is in degree centigrades or kelvins, Kelvin, and then S is the salinity here. S is salinity. So this is actually according to modern measurements of, this is a representative of the amount of the salt that is dissolved in seawater, but modern measurements of salinity is based on conductivity measurements. Hence there is actually a ratio of the electrical conductivity, it's inferred from the electrical conductivity of seawater. Hence this is a unitless quantity. This is unitless. This is also a common practice to say that salinity units or mention salinity units in terms of practical salinity units. This is again, I mean, it's a unitless quantity, but in more correctly, this is a unitless quantity. Hence, you can just state a number to determine to denote salinity. However, if there are other variables which we might be confusing, then it is sometimes necessary to state that it's in practical salinity units. Okay, I mean, this is also related to the measurements of grams per kilo, I mean the grams of salt per kg of seawater, and both of these are related. So that is parts per thousand grams per kg of seawater, and this is the modern measurements is based on conductivity measurements, and both of these are actually very close numerically, but are obtained using different techniques. Okay, so this is necessary for us to understand, because if we go into these areas, we will be routinely go into higher studies in these areas, you will be routinely using temperature and salinity measurements to start your process of analysis. Salinity is of course measured in the oceans. Temperature is measured both in atmosphere and in the oceans. So having this brief discussion related to salinity, at least. Now there are two terms which need a brief introduction, are alpha and beta. Okay, so what are alpha and beta? Alpha is the coefficient of thermal expansion. Okay, so this is the coefficient of thermal expansion, alpha equal to 1.7 10 raised to minus 4 Kelvin inverse, and beta is the coefficient of Hélein contraction. Hélein or saline, so anything is fine. So the beta has a value of 7.6 10 raised to minus 4. Why is it called expansion and contraction? Because the quantity expands. I mean, water, in this case, the ocean, seawater that we are considering, seawater expands as it heats, whereas this density decreases now. Whereas in terms, if you increase salinity of the same quantity of seawater, its density increases. Okay, so both of these work opposite in terms of contribution to density. So this is for seawater. Now for air, okay, so air is compressible air is compressible, and dry air behaves approximately as an ideal gas. Okay, so we are trying to find the equation of state. So dry air behaves approximately as an ideal gas, hence we can write the density as P over RT. Okay, so density is equal to P over RT, where R is 287 meters square per second square per Kelvin at ordinary temperature and pressure. okay, and T is in kelvins. However, we said that this is, we are assuming it to be, I mean, we are saying that this is a dry air. However, real atmospheric air is slightly more complicated than dry air. Atmosphere contains water vapor. Atmosphere contain water vapor too, and then the equation of state, I mean, this is of course the real situation. Atmosphere contains water vapor, and this is how clouds form, rainfall happens. We all know. So if we include the effect of moisture, if we include the effect of water vapor, this deviates from the ideal gas law, and this the equation of state has a form 0.608 Q. So we have introduced a new term, which is new variable, which is Q, and this Q is the specific humidity. Okay, this is the mass of water vapor mass of dry air plus mass of water vapor. Okay, so we have introduced a new variable, which is Q, which is the mass of water vapor by mass of dry air plus mass of water vapor. Now, even though we set out to find the relationship between density and pressure, we wanted to find out a simple relationship to between density and pressure, we introduced new variables like temperature, salinity, specific humidity in terms of this variable Q. So these are new variables that we have introduced, and we have no idea what to do with these at this point. I mean, unless we have something, some governing equation, we don't know how to deal with these. Okay, so these are new variables that we have introduced. So, and we don't know their dynamics, so we need to close those equations. We need a form of the governing equation for those equations for us to have a closed form of relationship between pressure and density. Hence we need additional equation. So we will start with the energy equation, which will help us in getting to that. We start with the energy equation. We'll state the first law of thermodynamics first, before going further. This, of course, is a recap. All of us know the first law of thermodynamics. The first law of thermodynamics state that the internal energy of a system is equal to the heat put into the system minus the mechanical work it performs. Okay, in mathematical form, we can write down the total change in internal energy as the difference between the heat and the work done. Okay, heat input. So describing these variables. So E is the internal energy, per unit mass. Q is the rate of heat gain per unit mass, and W is the rate of work done so think a better way to write is per unit mass. Okay, these are the description of the variables that we have discussed in the mathematical form of the first law of thermodynamics. Now the internal energy, there's a reason why you're doing this. So the internal energy is proportional to the temperature. The internal energy is proportional to the temperature of the system. So in E equal to CVT. So these are all first course, and these are from first course in thermodynamics. All of us know this. Is just a recap. What is CV? CV is the heat capacity at constant volume. CV is the heat capacity of constant volume, and T is the absolute temperature. Okay, so for air, CV is 718 joule per kg per Kelvin, and for seawater, CV is 3990 joule per kg per Kelvin. Okay, now using the law of conduction, Q equal to kT by rho del square T, which is the Laplacian of Laplacian operator. So this, in this expression, kT is the thermal conductivity of the fluid. Okay, and the work done by the fluid due to expansion is P dV dt. So here P is the pressure which is acting on the system, and this inverted V cut that I have written is volume per unit mass. That is, it is effectively 1/rho. Hence, the first law of thermodynamics writing it on the next slide, is Cv the total derivative of temperature is equal to kT by rho del square T minus P dV dt. Fine, this is the mathematical form of the first law of thermodynamics. This is equal to kT by rho del square T minus, this plus P by rho squared d rho dt. Okay, now, so this is the form of the first law of thermodynamics and we will use the continuity equation now. So we have already derived the continuity equation in conservation of mass. We rearrange the above. We rearrange the above form of the first law of thermodynamics, and this is what we get. So we get rho Cv total derivative of temperature plus P del U del X plus del V del Y plus del W del Z kT del square T. Okay, and the reason why we have highlighted this is because this is the energy equation. This is the energy equation, and this is applicable for both compressible and incompressible flows. Is applicable for both compressible and incompressible flows. However, for incompressible flow, as we know, the divergence, the velocity field is restricted to have a certain quality, and this quality means this term should go to 0. Okay, for an incompressible flow, we must have the divergence of the velocity field going to 0, and this means we have rho Cv, the energy equation, is equal to kT del square T. The reason why we have done all of these is to get to a form of the governing equation for temperature and other variables. We'll continue with governing equations for salt and moisture later, but this is what we have achieved, that we have achieved an evolution equation for the evolution of temperature. And this is needed because in trying to relate the pressure and density, we had introduced these new terms, new variables, temperature and salinity and moisture, and we didn't have an idea of what is actually going on there. And using the first law of thermodynamics, we now have a form of the temperature evolution equation. Next class we will discuss the governing equations for the salt and moisture also.